Section 2-3 we break up into two parts. The first part, we're going to talk about using long division to divide polynomials by other polynomials, looking at synthetic division to divide polynomials. And then in the second part, we're going to get into the remainder and factor theorems and the bounds test to find zeros. So long division of polynomials. If we were to have the graph 6x cubed minus 9x squared plus 16x minus 4, which is the picture right here. If we look at the graph, it looks like x equals 2 is a 0. And if we were to plug a 0 in for this x and we get, if we would plug 2 in for that x, and we get 0, then we know that x equals 2 is a 0 of that polynomial. Which means then if x equaled 2 is a 0, if we were to move the 2 over to the other side and write it in factored form, x minus 2 would be a factor. So what that means is that if we were to take this polynomial right here that gave us that whole graph, it would mean that to get that polynomial, we would have to take x minus 2 times some other polynomial. And so to do that, what we would do is we would divide our 6x cubed minus 19x squared plus 16x minus 4 by this factor that we found by looking at the graph. So if we were going to do that, this kind of already has the solution written out for you, but we're going to talk through it. So the first thing you do is we take this polynomial right here, and that's what goes underneath your dividing sign. And then whatever our divisor is, so in this case, it's going to be that factor, that x minus 2, that goes out here in the front. And we're trying to figure out if we were to divide that whole big 6x cubed polynomial by x minus 2, what would we have left? What would be that other polynomial that we could potentially multiply by? So what happens now is we take the first term right here, which is x, and we look at this term and you say, what do you multiply x by to get 6x cubed? And you would have to multiply x times 6x squared. So that's what goes up on top of your division sign. And then we take the 6x squared and we multiply. So we do 6x squared times x, and we get 6x cubed. So that goes underneath. And then we do 6x squared times negative 2, which gives us negative 12x squared. And we're going to line up all of our like terms. And then you have to subtract. So then if we were to subtract and subtract, we would get the negative 7x squared, and then we could bring down the next term plus 16x. You really can bring down all the terms if you want. So then we start over again. So now we say, what do we multiply x by to get negative 7x squared? And we would say negative 7x. So that's where this comes from. And then we multiply negative 7x times x is negative 7x squared. Negative 7x times negative 2 is plus 14. So when you subtract, you get 2x, and then that minus 4 comes down. Start over again. What do you multiply by x to get 2x? We multiply by 2. Distribute that, so you get 2x, 2 times negative 2, negative 4, subtract, and we get a remainder of 0. So here it says use the result to factor the polynomial. So what that means is this polynomial, 6x cubed minus 19x squared plus 16x minus 4 would factor into x minus 2, we got that from the graph, times our answer that was at the top, that 6x squared minus 7x plus 2. So we can use that long division to help us factor as well. So the division algorithm, the way that sometimes this is written out is you have your f of x, that's what the original function is that you started with. You have your divisor, so in that last example, that would have been the x minus 2. Your quotient is what you end up with when you divide the dividend by the divisor. And then if you had anything left, you would say plus the remainder. So in this case down here, this last thing you have left down here is your remainder. So in this case, we had nothing left. So for that example, we would say plus 0, or you wouldn't have to say anything. So when the remainder is 0, or the degree of the remainder is less than the degree of the divisor, then that's kind of what tells you what you're done. If the remainder is 0, then the divisor divides evenly into the function, or it's a factor of the function. Another way that you can write that long division of polynomials, we won't do this a lot, but you can say you have your function divided by the divisor equals whatever the quotient is plus the remainder divided by the divisor. So in general, before you divide polynomials, you need to write the dividend. The dividend is your original polynomial. So you write your original polynomial and the divisor, right? This is what you're using to divide. And you have to write it in the order of descending powers. So it starts with the highest degree. What that means is that that's going to go from the highest degree to the lowest degree. So you want it to go in order. And then if you're missing any terms, so like if you had a polynomial that was, let's say we had like f of x equals 3x to the fourth plus 2x squared plus x minus 7. If you were putting that in order, it would already be in order, but this part, this inserting placeholders with 0 coefficients, if you notice, we don't have an x cubed, so you would actually want to write this as 3x to the fourth plus 0x cubed plus 2x squared plus x minus 7, because then it just helps to hold the place when you're doing that subtraction, and it will help us in this next thing with the synthetic division as well. So synthetic division is just kind of a quick shortcut for long division, but it only works when the divisor is in the x minus k form, where k is a constant. So like x minus 3 or x plus 2, right? So that it has to be that linear form, two terms. The first one has a leading coefficient of 1, and then we could use synthetic division. So when you use synthetic division, what happens is we have a polynomial, so like an ax cubed plus bx squared plus cx plus d. And what we do is we list the coefficients, just the coefficients from our polynomial. If we're dividing by x minus k, then we put this value, the opposite in this case, because it would be like we're solving for k. So we would put that over here on a shelf, and then we start and we bring the a down, whatever that first one is down, we multiply those together, we put that here, and then we would add, right? And then you would just keep going from there. So let's do a practice here. Something to remember is that the very last term of your answer for synthetic division is your remainder. So if we're using synthetic division to divide x to the fourth minus 10x squared minus 2x plus 4 by x minus 3, then that would really mean that we're using x equals negative 3. So in a way you could set that equal to 0. So when we're doing this, that negative 3, I say we put that on the shelf. And then we're going to write the coefficients from this polynomial. And if we're missing anything, like we don't have an x cubed, we're going to hold its place with a 0. So we're going to say 1 x to the fourth, 0x cubed, negative 10x squared, negative 2x, and then 4. Leave a space. So now the first step is this first term, this 1 here, could just drop straight down. So that's a 1. And then we do negative 3 times 1, and we get negative 3. And then we add these together. And then we do negative 3 times negative 3, and we get 9. And we add these together. And then you do negative 3 times negative 1, and you get 3. We add these together. Negative 3 times negative 1, we get negative 3. We get 1. And I always kind of put a little box on that last one, because this is my remainder. Now, with your synthetic division, we don't leave it in this form. You have to go back to polynomial form. So this is your x to the 0 term. This is your x to the 1, x to the 2, and x to the 3. So when we divide it, we find out that our quotient is x cubed minus 3x squared minus x plus 1. And then that means then that we have a remainder of 1. Or you could write it that you have x cubed minus 3x squared minus x plus 1, and then plus the remainder. So you put the number of the remainder and then over whatever you divided by, which in this case was your x plus 3. So sometimes you'll see it written that way, where this is that remainder. You have one part of that x plus 3 left over. All right, that's technically the end of day 1. I'm going to move right into day 2, but if you just needed day 1, you can go ahead and pause and get going on day 1. The second part of this is the remainder theorem and our bounds test. So what the remainder theorem says is that if a polynomial is divided by x minus k, then the remainder is whatever value you get when you plug k into your function. So here in this first example where it says use the remainder theorem to evaluate this function. So what we're going to do is if x equals -2, then f of -2 would be 3 times -2 cubed plus 8 times -2 squared plus 5 times -2 minus 7. And if you were to calculate that out, you get -9. So what we find out is that the remainder is -9 if, in this case, what we were doing was if we took x plus 2 and we divided it into 3x cubed plus 8x squared plus 5x minus 7, we would find out that with that division that the remainder is -9. It doesn't tell us what the quotient is, it just tells us what the remainder is. So another theorem is the factor theorem, which is this exact same process as the remainder theorem, but what it says is that if you get 0 when you plug the number in, then that x minus k is a factor. So if we were to go back to this previous example we did, when we divided this polynomial, if we were to divide this polynomial by x plus 2, and we get the remainder as -9, then that means that x plus 2 doesn't go into this polynomial evenly because the remainder wasn't 0. Now, if the remainder was 0, then we would know that it goes into it evenly, and that x plus 2 would be a factor. So if we have to show in this example that x minus 2 and x plus 3 are factors, we're going to use that remainder theorem, or that factor theorem, to show that if we have x minus 2, then that means that we're plugging in +2, and x plus 3 would mean -3. It's almost like the number that you're putting on the shelf for synthetic division. So if we did f of 2, and we have 2 times 2 to the 4th plus 7 times 2 to the 3rd minus 4 times 2 squared minus 27 times 2 minus 18. If we were to simplify that, we would get 0, which would mean that x minus 2 is a factor. And then if we were to do f of -3, where we have 2 times -3 to the 4th plus 7 times -3 cubed minus 4 times -3 squared minus 27 times -3 minus 18, we also get 0. So x plus 3 is a factor. So now it says find the remaining factors. So if we have this 4th degree polynomial and we have 2 factors, what we're going to do is we're actually going to do synthetic division to find our other factors, and we're going to do it twice, which is pretty exciting. So you can start with either 0. So in this case, I'm going to start with 2. So if I put 2 on the shelf, with this polynomial, I use my coefficients, and I have 2x to the 4th, 7x cubed, negative 4x squared, negative 27x, and negative 18. And I do my synthetic division. I know the remainder should be 0. So if it's not, then you need to go back and check your work. So bring down the 2, multiply, and add. Multiply, add, multiply, add, multiply, and you get a remainder of 0, so that's good. So now what we're going to do is we're going to take our next 0, we'll use red, when x is negative 3, and we're going to put negative 3 on the shelf with these coefficients that were left over. So we bring the 2 down, multiply, 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 and we get another 0. So now we're left with 2x squared plus 5x plus 3 as our other factor. Remember, we could write that then with x minus 2 and x plus 3. So then the only thing you have left to do is decide, can you factor that 2x squared plus 5x plus 3? And what you find is that it actually does factor again into 2x plus 3 times x plus 1, and then times x minus 2 times x plus 3. So that would be how you could actually factor out that 4th degree polynomial given 2 of the factors to start. All right, so the remainder and factor theorems, using the remainder in synthetic division, just kind of that reminder that the remainder gives the value of that x equals k if you were to plug k back into your original function. Remember that if the remainder is 0, then whatever that k value was, you can write that x minus k is a factor. And if the remainder is 0, then k0 is also an x-intercept. So then the last thing we have to talk about are upper and lower bound rules. So what happens is sometimes you'll find zeros of a function, but you might not find all of them. And so in order to determine if you're finding all of the zeros, what we do is this bounds test. And so if you're doing the upper bound, if you think you're seeing all the zeros, what you do is you pick a number to the right of where that last 0 you're seeing is. And when you do synthetic division, if the last row of numbers is all positive or 0, then that means that there's no zeros to the right of any of the zeros you're seeing. And then again, if you pick something to the left of the zeros, what happens is if that last column alternates positive and negative, or that last row alternates positive and negative, then you know that whatever value you picked is a lower bound. So it just sets those limits as like there's nothing else outside of your set of rules. So here's kind of an example. First, let's verify that x plus 1, x minus 1, and x minus 2 are factors. So remember, to verify those, we're going to substitute in a -1, a 1, and a 2 into our function and show that we get 0. So if we did, this was supposed to be -1. If we did f of -1, and you did 3 times -1 to the 5th, minus 4 times -1 to the 4th, minus 10 times -1 cubed, plus 10 times -1 squared, plus 7 times -1 minus 6, we get 0. And then we do the same thing for f of 1. We can plug those in: 3 times 1 to the 5th, minus 4 times 1 to the 4th, minus 10 times 1 cubed, plus 10 times 1 squared plus 7 times 1 minus 6. We also get 0. And then if we verify that last factor, x minus 2, we would plug in a positive 2. So 3 times 2 to the 5th minus 4 times 2 to the 4th minus 10 times 2 to the 3rd plus 10 times 2 squared plus 7 times 2 minus 6, we would also get 0. So then the second part here is we're going to verify that -4 and 5 are the upper and lower bounds. So what that means is that if we were to graph this, we know that we have zeros at -1, 1, and 2. And so what we're saying is that if we were to go 2, 3, 4, -4, and then 3, 4, 5 to here, that if we were to kind of set boundaries there, we're going to do this bounds test to show that this point right here. So in these bounds problems, you will see they'll give you kind of that lower and upper bound that you're trying to verify. So in this case, this -4 is the lower bound. This is what we're trying to verify, that there's no zeros to the left of that. So we're going to set up our synthetic division with -4 and with this original polynomial that we had. So we'll have 3, -4, -10, 10, 7, and -6. And what we're looking for the lower bound, since this is our lower, we're looking that these numbers down here are supposed to alternate positive, negative. So when we bring down the 3 and multiply, and then we get -16 and multiply, and then we get 54 and multiply, and we add those, remember, so then 206, we get 824, so we get 831, and then we get -3324, so we get -3330. And so if you notice, they alternate positive, negative, positive, negative, positive, negative, which would mean that -4 is a lower bound. So then if we go to do the upper bound, in this case, we chose 5, or you were given 5, we do that same thing. We're going to have to erase just a little bit of this. And with the upper bound, we do that same synthetic division. So 3, -4, -10, 10, 7, -6. But this time with the upper bound, we're looking for all positive numbers. So if we get all positives, then we know that whatever number we picked there is the upper bound. So we get 1182. Our numbers can get kind of big if we pick a number that's kind of far from wherever we think we're supposed to be. So if you notice, these are all positive. So then that would mean that 5 is the upper bound. So what that bounds test tells you is that all real zeros have to be between -4 and +5. And then our last example here, finding the zeros of a polynomial. They don't give us any zeros. So what your first step is going to be to graph it. So go ahead and pause and graph this polynomial and see if you can pick out any kind of integer zeros. Okay, so from your graph, you should be able to see that there's 3 real zeros, but the only one that's the nice integer 0 is at x equals 2. So x equals 2 is a 0. The other two, if you tried to find them, are decimals. So we're going to, and then there was also that x equals 0 was also a 0. Because what we could do to get this x equals 0, if you notice, you could actually factor out an x, that GCF. So that way you're left with 10x cubed minus 15x squared minus 16x plus 12. So for finding all zeros, we already have it factored. So that's x equals 0. If we were to graph this 10x cubed, we would get x equals 2 as a 0. So now what we're going to do is synthetic division with that 2 and with the 10x cubed. So we have the 10, negative 15, negative 16, and positive 2. When we do synthetic division, 2 is a 0, so we should get a remainder of 0. And this was supposed to be a 12, sorry, from right here, 12. So when we multiply, we get negative 12, so we get a remainder of 0. So finding all the zeros, we have 2, 0, and then we also have this quadratic 10x squared plus 5x minus 6. And if you were to graph that again, you would get a parabola and it still has these decimal zeros. So what we have to do to find the zeros is we have to do quad form. So we're going to say x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And so we get x equals negative 5 plus or minus the square root of 265 over 20. And so if we do negative 5 plus root 265 divided by 20, we get 0.56. And if we do negative 5 minus root 265 over 20, we get negative 1.06. So those would be your other two approximate zeros. If you had to leave them exact, you would just write them in that form.